Thank you, Parker, I think, and you're welcome. So it's a great pleasure to be able to speak to you. I'm very sorry that I can't be there in person. I was looking forward to this for quite a while. Um, See some new people, see some old friends, be one more time in Bangalore, which is a wonderful city. But I had some family issues which intruded on that. So uh, I'm giving three talks. It's not so bad today for me. It's 7:45 in the morning. Tonight at 12:30 in the morning, I'll give Wednesday's talk. So this is a long day, and so we will see how that goes. But anyway, let me get started. So I wanted to talk about basically, I wrote a long title, but it's really about harmonic maps from surfaces. I'll try to write clearly. I don't know. Someone should scream. Parker, you're in charge of screaming in case it just the handwriting and the zoom just and the writing on glass just gets out of control. Okay, so this is really harmonic maps from surfaces, asymptotics. And as I said in the abstract, I'm going to try, even though I haven't finished writing the lectures.
Can you hold on a second?
Yeah.
Can you turn on your laptop video and then turn off your iPad video? Because we can't see you at the moment.
If I turn off, I see. Turn on the iPad video. Okay. Let me see if I can figure this out. See, harmonic maps. Ooh, that doesn't work. No. Uh-oh, I just really lost myself there. No, shoot. Nope. Now I've really gotten messed up. Here's the talk. Let me think how to do that, Parker. Oh, let's see if I do this. Uh-oh. Okay. Turn on. What do you want me to
start video?
For which one?
The bottom left corner, start video. It's currently
on the iPad?
Yes, on the iPad.
Okay. I cannot start my video because my host has disabled it.
Can you also remove the ICTS from the bottom corner? Just
Remove the
minus sign.
Click the
blue minus sign on the right side.
I don't see a. Oh. Yes. Okay.
Good. All right. Halfway there.
Halfway there. Okay. Now you want me to start the video over here?
Yes. Oh, that's good. Perfect.
Okay. And now I have to get back to where I was.
All right. Amazing. Yeah.
So you get to watch me from the side, though. Okay. Okay. So, the last time we spoke, we were speaking about harmonic maps from surfaces, and I'm really interested in the asymptotics. It'll take a little while to get there, and I'm going to try mostly to make this a tour of technique because that almost never gets done. And of course, along the way, there may be some results, but technique. And I at some points, I think after the first lecture, Parker, Charles, Franz, someone, Rukmini will take me aside and say whether I pitch this at the right level or not, and that will influence the next talks. Okay, because I can't see you to know whether to go faster or slower. So Parker, you can yell at me. Okay, so topic 0, just the basics of harmonic maps from surfaces. And I'll start all the way back from Riemann surfaces. I can write a little more slowly here than. Okay, so the energy of a map, say U from M to N, these are Riemannian manifolds. So maybe M is Gij dxi dxj. Maybe N is H alpha beta du alpha du beta. And so the energy is classically the integral over M of 1/2. We can write this in a number of ways, du squared with respect to the volume on M, or sometimes this part of the middle might be called the energy of the map U. And what is that energy? There's a number of ways of saying it, but what we could imagine is we have some unit frame on M, EI. We push it forward by the map U, and then now I have a vector on N, and then I take on N the metric H and I square it. I put a half out front because I always do, and integrate with, and then add it all up with respect to the volume measure on M. Okay, that's the energy. Now, in general, I'm still staying on energy. I'm not extremizing anything. So maybe if G, I want to quickly get to surfaces, is a conformal metric. Oh, it's not going to work. So, in this case, I'll write G to be, depend on a point. I'm on a surface, so I'll let Z be the coordinate, and I pretend I have a complex structure. So it's dz squared, or if you like, dx squared plus dy squared. Z is x plus iy. And so if I write that, then of course the first frame element is dx. Okay. I saw camera switch, but that's okay. Dx over, the length of x. So in this case, it's dx over square root of g. And so that means that this energy would then be, 1/2. I'm just going to highlight something. You push forward dx squared at h, normalized by this length g squared. Same thing for dy. Push by g squared. And then the volume form is, of course, g dx dy. And I write all this out so that you can see that the metric on the domain cancels. And so, in fact, there is no dependence on the metric on the domain. The whole thing is just the the integral of the square, the push forward of a frame. And so that's the energy for a Riemann surface. Okay, so in other words, the energy just depends on the conformal structure. So it's just the energy of a map from a Riemann surface, not a Riemannian surface. Okay.
Can you move the video off on the iPad? Just slide it.
No, it's not sliding.
On the bottom right corner of your iPad, just move that video out.
Oh, this thing.
Yeah. Can you slide it out? Yeah, perfect. Thank you.
Okay. Okay. It's so nice to have a set director. Okay. So one problem with the iPad is I now have to go to the next slide, and all this will vanish, I'm afraid. So so I'll just summarize, though, that what we saw was that the energy depends only on the conformal structure of M. And so maybe I'll start writing this energy as a Riemann, and script R, Riemann surface to N. Okay. So what's a harmonic map? Harmonic map is a critical point for this energy of U. Harmonic map, say U, from R to N is a critical point for this energy functional in some homotopy class. So Okay. So the Euler-Lagrange equation, which we won't have that much use for, but I'll say the Euler-Lagrange equation, it's a variant. It's a Riemannian version of saying the Laplacian is zero. It's actually the Laplacian if n is flat. And so maybe I'll just write it as tau of u equals zero. And if you really insist in this coordinates, tau of u looks like the Laplacian plus some correction term. Let's see. So this is u gamma, u alpha, z, u beta, z bar equals zero. We won't have much use for that coordinate. So I'm just sort of pointing out it's the Laplacian. So, and the meaning of this is that we don't want to get too far into the symbols and too far from the geometry, that the sum of acceleration vectors of u, so take a frame, look at some curves through each of the frame elements that the parameterization the frame gives you, push those curves forward, take their accelerations, add them up, the sum of the acceleration vectors vanishes. So that's maybe how to think about this at first. Now, this is an Euler-Lagrange equation. It's going to have it's a divergence form. Anyway, so there'll be we expect a conserved quantity. So as I said, we might think of this as being written in some um, rough way as u z bar equals zero, Laplacian equals zero, and I'll just point out that we rewrite that as u z bar equals zero. So what you see from this is that in the very basic flat case that we have a conserved quantity. So uz is holomorphic, and I like the point of view that this is a conserved quantity. Because I had up here a second order equation, and now I have a first order equation in z bar for something else. Okay, and so that new thing is something to look at. So we have this sort of conservation law that the z bar derivative of uz vanishes. So in the more Riemannian setting, the conserved quantity is the Hopf differential. So I don't know, more directly or more correctly, maybe, um, more precisely, uh, we have this. We have a Hopf differential. Okay, so that's a technical word, and maybe I'll call it Q. And you can, if you want to know what it is, it's basically uz squared, but in the proper way of writing it is uz bar bar dz squared. And the point is that this is holomorphic. So that's a first order condition. All right, so I emphasized these that we don't want to stray too far from the pictures. So we can ask, what is this object in pictures? What are any of the pictures? Okay, so moving to the next slide. So the pictures are, so for the energy, I take a frame on M and I push it forward by du, and oops, it shouldn't have gone that way. And I get some frame on n, which is no longer orthonormal, and the energy is the sums of the squares of the stretches, right? Now, Now the Hopf differential is a holomorphic quadratic differential on a Riemann surface, and all of those have a picture. So there are some famous pictures. Handwriting's starting to decay. Sorry. So just in general, if I have a quadratic differential, q, which I can write in coordinates as q of z dz squared, I can change coordinates from a z coordinate to a zeta coordinate. So let me back that up. So I go from z to zeta, and the zeta coordinate I want to use, I'm going to do this away from the zeros of q. So I can take a well-defined square root. There's two of them. I'll make it dz squared and put a plus. So I have a plus or minus, and that'll make sense in a neighborhood as long as I'm away from a zero. Integrate it, I get zeta. And then the point is that zeta is a canonical coordinate, because in this coordinate, by the fundamental theorem of calculus, q of z dz squared can be written as d zeta squared. Great. So what's the point of this? Well, if I have a Riemann surface, again, I have these zeros, and holomorphic objects, of course, their behavior is usually falls into two cases. Either you're at a zero or near a zero, or you're not near a zero. So the divisor of these holomorphic objects is the critical thing to study. And so I've said that we're going to be away from a zero. And so I'm some patch over here, and then the map zeta takes me down to the zeta plane. And in the zeta plane, we have horizontal lines and vertical lines. And because this coordinate is canonical, those lines are canonical. So they pull back to the surface, as some sort of pair of foliations. And that pair of foliations fits together at the zeros. The zeros are somehow critical, and we get patterns like this. And let's see, I'm in green. They sort of join up over in. Oops, that went somewhere else. Anyway, so they'll wind around the surface and join up like this. Come back up there. Okay, so and it's, as long as I'm pointing this out, I'll point out that there are two measured foliations. There's the horizontal foliation and the vertical foliation. And these, by this, I mean the horizontal lines. So this would be if zeta is psi plus I eta, then the horizontal foliation will be, the lines where eta is constant, the horizontal lines. And then there's a transverse measure, d eta, which counts how many of these lines you cross, so that if I had some curve, let's see, let's put one more blue line here. And then I have some curve that goes up, and then it comes down, and it goes up. And you see it's gone up 3 times, come down 2, gone up another 2. So its total variation with respect to this measure is 3 plus 2 plus 2 is 7. And so this measure counts this sort of crossing. And similarly, the vertical one is where psi is constant, and we count d psi. Okay, well, this is all very classical. This quadratic differential, these foliations, etc., go back at least to Teichel, or maybe to Groch, maybe further. It's really just a quadratic differential version of pictures you would get for a holomorphic one form. Okay. And So what does this mean for harmonic maps? So in the harmonic maps setting, what are these foliations? Well, the horizontal one integrates the directions of maximal stretch. And the vertical one integrates the directions of minimal stretch. So what I mean is that if you look at the differential du, it has a pair of eigendirections being mapped in between two symmetric matrices, basically the metric on the domain, the metric on the target. And one direction gets stretched the most, and there's an orthogonal direction that gets stretched the least. And the blue lines are integrating the directions that stretch the most, and the green lines are the ones that get stretched the least. And they meet at some point where they all stretch the same amount, and that's those are the zeros of the Hopf differential. So the Hopf differential is some auxiliary object to the map, and so the challenge is, of course, to understand to use the shape of the Hopf differential to understand the map, and maybe help clarify aspects of the geometry of the map, or at least understand how various maps have their various Hopf differentials. So it's just a central object. Okay, so those are the basics. There's a number, I should say at this point, I'm starting to get a little bit embarrassed because there are certainly members of the audience who have seen everything I'm going to say and can sing along with this sort of treatment, and because they've heard it from me at least many times and can probably say it better at this point. So my apologies for the repetition to those folks. Okay. So, at this point, everything is formal. So what's an example? So I think the most basic examples, and so I'm going to be thinking of examples of maps U from C to H2, and that seems very basic to me as a very basic domain and very basic target, picking something which is not flat in the target. So, and here's my very first map, which, we can check that it's harmonic, but I think you'll just believe it. I'm going to take C and I'm going to map it to R. So I have in mind C, and then C gets mapped to the real line. And if you like, I have Z in C, and I'm going to map Z, which is X plus IY, to its real part, X. And I think we agree that's harmonic. If anything's going to be harmonic, that's going to be harmonic. And then I'm going to follow this this map. I'm going to go over to H2, and I'll take this over to here by into a geodesic gamma. So this is a geodesic parameterized by arc length. Okay, as I say, the first map is harmonic, and the second map is an isometry of R into the geodesic. So if anything's harmonic, that one should be. Okay, great. So I said, let's try to understand the shape of this map. Well, this map's pretty simple, but so note the Hopf differential of this. And there's a number of ways of seeing what this is. So certainly this map from C to H2 is translation invariant. So the Hopf differential should be translation invariant. And so you can just abstractly conclude that the Hopf differential is a translation invariant quadratic differential on the plane The only one that could be would be dz squared up to some constant, which we would have to figure out independently. You could also just compute it. You know, I told you the formula, so you could compute that that Q is, I believe, 4 dz squared. You know, remember that the map here is basically real z. So if you like, it's z plus z bar over 2, and then you can just work out uz bar bar. Or you can note that the kernel of this map U is a projection. So the kernel of the map is vertical. So I would want the vertical foliation of the map to be the vertical lines in the plane. And of course, the vectors that are being stretched the most are the ones that have no verticality at all. So those are horizontal. So just from the foliation point of view, you can figure out that Q has to be dz squared. And again, pick one of the vectors, see how much it gets stretched, and put a 4 in front. Okay, so but we have learned that the Hopf differential has foliation, which is exactly this. You know, its minimal stretch direction or vertical foliation is vertical, and the horizontal foliation, the maximal stretch foliation, is horizontal. Okay. Okay. So, all right, I can't see anybody. So I can pause and see if there are questions. Hearing none, I go on. Oh, this point. Okay. Perfectly clear or perfectly dull lecture. I move on.
I'm sorry. Hi, Mike.
Hi.
Very nice beginning. So, is it very obvious that translation map will give you a translation invariant of differential?
Very obvious. Well, I don't know. The map, you know, if you slide along the plane, then when you project, my video's over here. So if you slide, so if I slide horizontally in the plane, I'm going to slide along the geodesic, but the geodesic's is a homogeneous object. So I'm not going to locally see any difference. And if I slide vertically,
Okay.
then I'm also not, then I'm not changing the map at all. And if I do both of them, I'm going to just slide around a little bit.
Okay. Yeah. Thanks.
Okay.
Yeah.
Okay. Anything
So
else?
question, let me, since Mike, it's Rob. Hi from somewhere nearer to you than Bengaluru. There's nothing important about it being H2, I guess. If you map to a geodesic,
Right.
and
That's correct.
wherever it lives,
Yep.
same difference.
I'm making things simple, and I also know what I'm going to say next. So there's a little bit of prep and foreshadowing.
Okay. The main thing is it's mapping to R first. The rest is
Right. Right. Absolutely. Absolutely. And that's, yes, that's fine. But I want to stay in the setting of, in general for today, of C to H2. Okay, with that, let me continue on then. So we've said, oh boy, let's go back. So I want to get a more complex map, and how should I think about making the maps more complex? Well, I started to emphasize this Hopf differential, and this Hopf differential is a constant. 4 dz squared. That's very, and it's, I'm going to always have in the plane some says holomorphic or maybe meromorphic function times dz squared. So what's the next most complicated holomorphic function? So I'm going to try to order complexity not somehow by the image, but by the Hopf differential. So in this case, the let's see, did I just make anyone? Yeah. So so the next example is, let's look for the next most complicated Hopf differential. So I'll put a single 0 here. And really I'm sort of at the same time going to be thinking about a higher order 0. But in this sort of analysis, it's not going to matter. But let's just think about a simple 0. And so, now working backwards, previously I said, oh, well, here's a map. I would start with a map and what's its Hopf differential. Now I'm going to start with a Hopf differential and ask what's the map. So what does this look like? Okay. Well, let's do a little bit of a thought experiment first. So we know that the Hopf differential, its shape in the plane, is going to look something like this. I mean, there'll be a central 0, and you can compute that there'll be 3 prongs coming off of this 0 that are singular, and everywhere else I just have some leaves. So, so if I think about this, I'm in the plane. I'm continuing to draw leaves, but if you think about being like way out here, well. At this point, the out here, the map is not feeling the presence of the 0 very much. The 0, from the perspective of this domain, is very far away, and so it's not exerting as much influence as you might as it does closer. And so the map, in some sense, and I'll just be what someone once referred to as American, I don't know. The map anthropomorphizes everything. So the map thinks that its Hopf differential is really, d zeta squared. Because that's what it looks like. So, and we've seen, that what is d zeta squared as a map. So, i.e., the map we imagine is nearly a projection onto a geodesic. So, so we might so how are we going to formalize this? Well, I mean, a natural 1980s thing to do would be to try to take some geometric limit. So, we look out here and we center our perspective at some point in the center, and then we go further out and we center our point, and just keep looking at the map further and further out as if it's the center of our point of view, take a limit. And what we'll have, we would hope, is that a projection, and we would learn that the that this map really is asymptotic as we go out to mapping to a geodesic. So that's a rough point of view, maybe from the 1980s. I mean, this requires. So I don't know how to summarize that, but so I'll just say take a geometric limit. But in order to do that, you're going to need some a priori bound to know that your projection isn't collapsing to 0 or blowing up to infinity. You need to know something about what the map looked like, something coarse out here in order to start to analyze it. Okay, so with that in mind, how do we start to analyze these harmonic maps on a non-compact surface? And complex plane is simplest such thing. Well, So let me point out a little bit more about harmonic maps from surfaces. So I can pull back. So again, I'm in the setting where I have a map U from a Riemann surface to N with some metric, and I can pull back the metric to the Riemann surface. And on that Riemann surface, I have a coordinate Z. And when I pull it back, I can decompose by type into some portion of the metric, which is dz squared, some portion which is dz bar, and some portion which is dz bar squared. And it turns out that the when you do this, the Hopf differential is the non-conformal part. So and the part in the middle, well, we know the part in the middle because it's going to be the sum of the squares of the stretches. So this is the energy made into a metric. So I'll just say G times the energy. And in fact, staring at this a little bit more, we can write this energy, or let me just say that what's the energy in conformal coordinates as the push forward of dz squared and the push forward of dz bar squared. And there was an influential article in the late 70s where this holomorphic energy was given the name script H. And when I write that as script H, then this becomes, when you figure it out, the size of q squared over H. And so why do I do all this? The point is that if you want to know this map, it's enough to know the Hopf differential and one other piece of geometric data. So if I know H and I know Q, I know everything. So the question is, well, and now I'm just telling you that we are given Q. I said that Q should be z squared. So if I give you Q, what is H? Well, there's some equation that relates the pair of them. And this equation and its form are sort of show up everywhere in this sort of analysis of harmonic minimal surfaces, other sorts of variational problems on Riemann surfaces, and so here's the equation, and I'll make a comment. So the equation is that it's easier to write h as e to the little h, can be more common. So in this case, it's 2e to the h minus 2e to the minus h q squared, and then something about the basic background metric, if I put a background metric. And what you'll notice here, especially in the coming week, is that there's a plus sign here and there's a minus sign there. And I'm really old, and so the privilege of being this old is that I get to pick the very best signs for my analysis, and other people are stuck with worse signs, and they'll talk. I'm thinking in some of the other talks, you'll see signs where the equation is not so nice, but this one, the signs are optimal. And I'll call this equation B. It's often called a Bachner equation. In other settings, in other guises, there'll be versions of this, a new version coming up later, where it's really an integrability condition for a map. And this is why it arises so often. This is a Gauss equation. Okay, so this is my equation. Let me copy it on the next page and keep talking about it. So this equation B, as I said, is Laplacian H equals to e to the h minus 2 minus h q squared, and then some curvature term. Okay, so now, and the point is again, is if you just remind you, why do I care? If I know Q, this equation solves for H. If I know Q and H, I know everything. You notice, let's see. Now, some notes on this. Q through equation B determines H, and that determines the map. So that's one. Two, this right-hand side is convex in H. That's helpful. And so for this reason, this admits, well, actually, separately, this admits a maximum principle, this equation. And what's really important is that if you think of this, as Laplacian H, and what's just abstractly, what's the right-hand side depend on? It depends on, a position Z that's going to determine, so values of Q, values of the curvature. And it also depends on H, and that's it. And the important point about this is that if you look at that there's a monotonicity on the right-hand side, that the derivative with respect to H term is positive. This makes a lot of stuff work very nicely. So, and then, like I said, that once you know H and Q, you know everything. What you notice as well is that so this right-hand side is rotationally invariant in the sense that I'm just looking at the absolute value of Q squared. And so if Q, it looks like Z to the K dZ squared, then the absolute Q is, R to the K. And so this equation would then be just rotationally invariant. And it really an ODE in our case, which you could then try to solve. And let's see, I think for K equals 1, this is Pan-Lavey. But really the point is that the H, these H functions are norms. And so, but the Q is not. The Q, as we've seen, has a foliation structure. It matters whether you're going at an angle 0 or an angle 30 degrees. That has a different value for Q itself. The norm does not. But the H is only seeing the norm in the equation. So the interaction between the two is an interaction between a magnitude and a direction, where the direction is coming from Q and the magnitude is coming from H. Okay, so maybe I'll write something like that. So H in some sense is a magnitude, but the Q has direction. And that's part of the interaction. Okay. As I said, we need a bound for this map to understand this map. And I've chosen a very basic example of C, which alas, or fortunately, unfortunately, is not compact. So how are we going to work with non-compact domains? And so now we transition to some PDE theory. in order to get the bounds. And so the point is that, I will remind you, the setting of this equation is I have Laplacian H is some function Z and H, and we know that this function with respect to H is positive. Well, and so the PDE theory is this. So if we find a super solution, H upper bar, and by super solution, what I mean is that, what do I mean? That Laplacian H upper bar is less than this H bar, or if you like, Laplacian minus F applied to H bar is less than or equal to 0. If I find a super solution and I find a sub-solution, H lower bar, so Laplacian minus F lower bar, this is F of lower bar, is greater than 0, and I find them in such a way that the super solution is bigger than the sub-solution, then there exists some solution, it's an actual solution, H, on this whole domain with the estimates that H is bigger than the sub-solution and less than the super solution. And here these sub and super solutions are weak. And you should really probably be thinking of, the Perron process, where, for example, a max of 2 sub-solutions is a sub-solution. So, you have one graph, I don't know how to do this schematically, going down, some other graph going up, H1, H2, and you can take the maxes of them, and that's a new sub-solution. You can sneak up on this thing from underneath. Okay. So, a lot of my shtick is to take some abstract off-the-shelf PDE theory and then try to use it to understand shapes of the maps. So what this is saying is, basically, if you can make a good guess about what the map U looks like, so in this case, i.e., what this function H looks like, you can prove your guess. So you take your guess about what this holomorphic energy should grow like, and if you can get under it in some way with a guess and get over it in some way with a guess, then you can prove your guess. So so let's do that. So maybe this was sufficiently fast and maybe sufficiently different that I should pause again for questions. I have 9 minutes, I think. So Parker, can you call for questions?
Any questions from the audience?
Thank you, Parker. Okay.
So I had a question, quick question. So sorry, sorry. So
I'm out of time.
you are going to take various Qs and solve for H. Is that the plan, or?
No. Thanks for the question. So let's see. So my equation, I'm going to rewrite. Let's pick a different color. Remember, the equation is Laplacian H equals 2 e to the H minus 2 e to the minus h q squared. I'm on C, so that's it. Okay. Now, q is fixed. So I started with q being z dz squared. So q is given, and I want to find h.
Okay.
So in this, I started with this like simplest example, and so I made it very, very complicated. I actually have a plan. I don't know if it's a great plan, but I wanted to start with something simple and then do something a little more sophisticated, which is more general. So Q is given, and what is H that depends on Q? And I already know Q. If I can find H, then I know the map.
Right.
Does that make sense?
Yes, got it.
Okay. Okay, so let me go on. And so, well, let's see, a little bit complicated here. Maybe, I wonder if I can do this. Ooh, look at that. Can you, have I made it bigger?
Yes, this is much better.
Yeah, but wait till you'll see what I'm going to do next. All right, so staring at this equation, I'll just point something out. If, for what should I call it? For maybe I'll say H star, just something else. If I take H star to be log Q, okay, then what happens? The right hand side becomes well 2Q, and the left hand side becomes 2Q, and I get 0. And the right hand side, if this makes sense, now I'm taking a log, so I never worry about zeros, but I didn't say that right. The left hand side is the Laplacian of log Q, but Q is holomorphic, so log Q is harmonic, so the Laplacian of that's 0. So in some sense, we know a solution away from the zeros. This log Q is a good solution. Is somehow we kind of expect that H should be log Q. And we can use that. And so you can take, switch colors, something else, blue. So I can take H bar to be some variant of log Q. So for example, and you can just check that this works. Now you have to play a little bit, but we know we want to get something that's like log Q, and this works. And now for the sub-solution, we could take just plain old log Q, and that will kind of work, but we have to worry about the zeros. So maybe that is once Z is beyond something. So this will be H bar. And then, for Z less than Z, now you have to fool around a little bit. Maybe we'll do, excuse me, back that up. The max of log Q, because I'm allowed to take maxes, and then I'm running out of room, some hyperbolic metric. So, why? I'm just going to point out, I go back to the equation. If I just looked at this part of the equation, so the equation, so maybe I'll put this in this color blue. Note that part of it, Laplacian H equals 2 e to the H, that's the equation for our hyperbolic metric. That's just the constant curvature equation. So, and then I'm subtracting something off of it. So if I want something positive, it's enough to like have a hyperbolic metric in here. So I'll just take I'll take like the hyperbolic metric near the zeros, and then I'll transition that into a log Q, and that'll be a subsolution. So I'm kind of I'm building something that's roughly right.
Mike, can I
And
ask a question?
if I build something that's, and what this technique does is it says that if you build something that's roughly right, you'll get something that's correct in between.
Mike, can I ask a question? So what
Sure.
do you mean by hyperbolic metric? I mean, don't I want a function? I guess you're taking the conformal.
Yeah, the hyperbolic metric density.
Okay, thank
you. Okay. So what this says, okay, so now let me shrink back down. Sorry for the small writing, but I put it all in one slide. So what do we learn? So, I don't like that color. So there exists a solution H to our equation B, and we get an estimate, right? It's in between the super solution and the subsolution. So, and we know, and those solutions are all basically like log Q. So we know that H is basically log Q as Z goes to infinity. So now I know Q, I know H. So this tells me what the map is. And remember, we had said that we were looking way over here where we expected this to be a projection. And sure enough, now way out here, where Q is basically constant, is Q is d zeta squared. So in this region, Q is like, d zeta squared. So log Q is like, so Q is like 1, log Q is like 0, H, the energy is like 1. And so what we're saying is that, so this map is, so U is like a projection with scaling exactly like the projection in example 1. Example 1. So now we know what this map looks like. Let's see. Getting myself. Oh, well, that's fine. So I skipped some steps here. I mean, really, what I probably should have done is said that U star ds squared on H2. Remember, was Q dz squared plus G e to the H plus e to the minus H of Q squared dz dz bar plus Q bar dz bar squared. And now you can just plug in that H is log Q and Q is 1, and you can find it's a projection. So this really turns out to be 4 dx squared. I should say it's like this. Okay. So what we're finding, so maybe more in general, so for example 3, which I was sort of doing at the same time, if I have z to the k dz squared, and I just did k equals 1, so that the picture, oops, don't want to do that. So that the picture, maybe looks like this, more complicated. And so maybe what I imagine doing is building myself some domain where I'll take some far out collection of these those horizontals, and I'll connect them up with some verticals. But remember, what the projection does is it collapses the verticals to nothing, and so it approximately collapses these verticals to almost nothing, and it's going to stretch these horizontals and just project them to a geodesic. So we know that the image, so what we're learning is that the image over in H2, which should close up, is going to be some polygon something like this with nearly geodesic sides. I guess I should have written it a bit wavy, and very short connections. And that's an approximate. And so then in the limit, what we have now basically proved is that the image is some polygon, and in fact, by the K-fold, by the dihedral, by the symmetry group here, we know it's a regular polygon. Q is z to the k, but so this is, we now know this sort of image, and we now prove what this thing looks like. Let's see. Oh shoot, I'm over time. I've actually proved what it is on the boundary. I haven't told you what it is in the interior. I guess I'll maybe say that next time. But the interesting thing, the thing I really want to highlight is, and I'll go to the next page to do this, and then I'll stop. So this image is this ideal polygon. And when we have, and this is coming from some shape like this, and this arc here is going right down the throat of this cusp. And when we have a change in behavior, or sort of very dramatic change in behavior, because on this side we are in this sector, we're mapping to this geodesic. And on this sector, trying to draw a different color, we're mapping to this geodesic. And as we change direction, change sectors from here to here, we have a rapid shift in asymptotics of the map. So on this bottom sector, we have a asymptotic solution, which is, we have a approximate for the harmonic map to be the harmonic map to this geodesic. And on this sector, we have the asymptotic solution for the harmonic map is this geodesic. And the two geodesics are sharing a forward direction in H2, but their backwards direction is different. And so there's a flip as we go across this direction from approximating asymptotic solutions. So this is very much like the Stokes phenomenon. that you find for ordinary differential equations, probably the first would be for area equation, e.g. And so this is kind of a theme that I'm going to develop a little bit more about these high energy maps or their asymptotics, where the asymptotics in a sector, the good approximation to a solution in one sector can flip to a different good approximation in a different sector as you cross sectors. So this is something we're picking up. All right, I ran late. I'm very sorry. I'll stop.
All right, let's thank Mike for a wonderful talk. Any questions?
I
Hi,
have
sir.
one question that's, sorry, go ahead.
Just one small clarification I just wanted to understand. So in that super solution, sub-solution slide, you are taking the derivative of f to be positive. Probably I missed, but where exactly did we use that the derivative is positive?
Oh, yeah. Buried in the words PDE theory.
Okay.
So this
Thank
is a theorem that if you have this in this setting, this technique works. And basically you have a maximum principle, sort of what's going to make things work. So with this, I think, basically we have a maximum principle, and so you do like an exhaustion. Oops, I'm gesturing over my tablet. So you have these two solutions, and then they give you also sub and super solutions in a subdomain, and then in the subdomain, your solution, you can find a solution with compact solution with some boundary conditions on the subdomain, and these conditions plus this say that on the subdomain you have the estimates you need, and then you take a limit and you're continuing to trap the solution between the sub and the super. Does that help?
He said yes.
Okay.
Thank you so much for this wonderful talk. Can I ask a quick question?
Sure. Flattery will get you everything. Okay, yeah.
So this the H upper bar and H lower bar, you said you can often guess from the geometry. I mean, okay, here it was log mod q, so obviously, but sometimes you said you can even guess it from the geometry. So what is the geometrical significance of?
Okay. I might have misspoken. What I'm saying is that if you can make a guess, and sometimes you're right and sometimes you're wrong, but you might have an idea what the geometry is. So you have this conception, you have this insight, like it
Right.
came, it came to you before you fell asleep. I don't know, some Greek oracle gave it to you, whatever. I mean, you found it on the street, and then somehow you come to a guess. And the idea is once you have your guess for whatever reason, you can, if you're right, this is a way of proving that your guess is right.
Okay.
So I had the intuition that way over here,
it will be a projection, yeah.
The map is not going to know that there's a zero. It's going to not feel the influence of the zero. Right. So my guess is that this was a projection.
Right.
And so I built a collection of H lower bars and H upper bars so that one would be a little bit bigger than a projection and one would be a little smaller. And because one was a super solution and the other one was a sub solution, I can now prove my guess was right. Because I have a, slightly bigger than a projection above, slightly lower than a projection below. But asymptotically, both were the same projection.
Right, right. So the geometry gives you an intuition of what to guess.
So you're trying to do geometry of maps, but unfortunately, you're doing this subject called harmonic maps, and a harmonic map is exactly a map which satisfies a certain PDE. So you can like think all you want about um, shapes that are being stretched or shrunk, and what is their energy, and what would be a map where the acceleration vectors would be in balance. You can think of all this sort of soft ways, but ultimately, if you're going to prove anything, you have to get back to the PDE. And so there's a collection of methods that let you get from however you're imagining the shape of the map to proving your guess, i.e., proving that the actual solution to the PDE has the shape you suggest, and this is one of the methods.
Okay. Thank you so much.
I have a question, Mike. So these guys are harmonic maps from the complex line into hyperbolic two space, harmonic. So there must be Gauss maps of something, right?
Yes.
Namely?
Constant mean curvature cuts in Minkowski space.
Ah, very nice. So that means that your equation is, as you said, a good one, because it say if the Q square were 1, you had no umbilic, say, the first example.
Right.
Well, there are more solutions probably, but you would see a kind of Sinch-Gordon equation, but it would have a minus sign in the right place in front of the Sinch, right?
Yeah, I mean, this can all be rewritten in terms of a Sinch-Gordon. I probably won't get it exactly right.
Yeah, it's Laplace H minus Sinch H is 0.
Yeah, actually, let's see. If you look at, let's see if I can get this.
I mean, if the Hopf differential is 1, if DC is greater.
If I look at, say, the function g, which is log uz bar squared over uz bar squared, then I believe it's Laplacian g equals since g may be a constant, and then if I did this right, q squared. Oh, I might want to put this as a minus. I think it's something like that.
Yes. Yes.
And so it really is sort of Sinch-Gordonish.
The other sign would be a harmonic map into the two-sphere.
Right. No, like I said, so Franz, we were both young, at the same time. I just took the one with the good sign and left you with the bad sign.
I know.
But, it's just, we're both paying the bills.
Right. You can make a living with either signs.
Yeah, right. It's right, a little, I just don't have to stress as much.
Thanks.
Okay, so let's thank Mike again. All right, and that's the end of today. And we'll see you tomorrow morning at 10 a.m. where we have Mike speaking again.
At 10. Okay, good. Yeah, 12:30 a.m. my time.